right, welcome everybody, and thank you again for joining us here at Ask Why, where we take technical challenges for our engineers and break it down Barney style. For today, we have aerospace and defense, and we're really trying to look at the components where failure isn't an option. So every component must operate flawlessly in harsh environments and harsh conditions. And that's why high reliability tantalum capacitors are built different, they're tested different, and they're trusted capacitor in mission critical systems. Today here I got James Turner with me, who is the product manager for our high reliability tantalum capacitors. And we're going to dive into what it actually means for a high reliability tantalum capacitor to come into existence. So James, let's start with the very basics. So why is tantalum the preferred capacitor technology in aerospace and defense?
Yeah, sure, Simon. In defense and aerospace applications, you've got this sort of mantra of size, weight, and power. Everyone's trying to downsize and miniaturize their system to lower weights, to fit more functionality into smaller board space. Tantalum really shines there because you've got a capacitor with the highest volumetric efficiency. You can get the most capacitance into a small space. And so, where it makes sense, if you've got limited board space, tantalum could be a really good choice for you. The other thing too is, the military defense applications, they're kind of required to work all over the world. You might have, applications where you're in a desert, really dry environment, really hot environment, or you might, be storing missiles or radar equipment up somewhere near the Arctic, so it's really cold, really dry, or maybe even somewhere humid. And tantalum really shines there just because you've got this capacitor that, relative to many other technologies, across temperature ranges, across a lot of frequency, or over a long period of time, that electrical performance is relatively stable and reliable.
So now YAGEO Group offers a pretty different reliability levels in tantalum capacitors. Can you explain a little bit of how these different tier structures are done?
Yeah, sure. With military grade capacitors, there's a history of having some sort of established reliability option available. So this is measured in like a percentage per 1,000 hours of performance. With commercial automotive grade, there's not really like a set reliability level. There's some expectation of reliability in commercial products, of course, but with military grade capacitors, high reliability, for MnO2, we've got YAGEO grading. For polymer, we have a Chemet developed process called the polymer capacitor reliability assessment test. And so what this can do is, for a given batch of part numbers, a given product, you can have 0.1% per 1,000 hours of reliability, all the way down to 0.001% per 1,000 hours of performance. And so, you think about that over the life, a long life of a product, we're guaranteeing some level of established reliability on that part. This is all, I'm kind of getting into the weeds a little bit about the math, but these are all kind of established in the mil specs, and you can read about how the math is done, how all of that is established in there. But basically, you're just giving the capacitors a grade of how well they're expected to perform.
All right, so how do we actually prove that these capacitors meet those requirements? I know you dove into this a little bit already, giving us some examples, but do you have some more?
Yeah. So those are the two main ones, the YAGEO testing or the polymer capacitor reliability assessment test. Those are the ones that establish that grade itself. That's really, there are other ways of having or showing reliability or building in reliability into a capacitor. There's ways of screening the capacitor so that they have more reliability on turn on. You weed out weak capacitors that might have failed in the early stages. There are processes here that we can perform on those capacitors as well to really extend that long life of the capacitor. So, for example, we've got surge current testing, which is a pretty pivotal, screening process that we do, which may weed out capacitors that have they might have some sort of weakness in the dielectric layer. And so by putting it through a surge current test, you're stressing the capacitor, and you're making it fail now rather than fail in application with the customer. We've also all got custom options that we can do, where we can really clean up the dielectric layer to extend the life of the capacitor. So over time, as a capacitor is being used, these microscopic defect sites, those are where it will start to the weakness will start to grow over time. There will be crystallization that happens. That's a site where leakage can start to happen. That's a site where a short can start to happen. So in our manufacturing process, we can do things that really clean up that dielectric layer to minimize the number of those fault sites and prevent them from growing over time.
So I think essentially what you're saying here is that the capacitor is from the ground up a completely different design from our regular components.
Yeah, absolutely. These are processes that we do here. We make our high reliability capacitors here in the U.S., where our innovation center is, and so we don't cut corners. And not to say that where commercial is cutting corners per se, but we can't afford to have any of those types of defects in these high reliability capacitors. You think about it, you've got military applications or space applications. The capacitors out there, you don't have a repair team that can go out there and service it whenever, wherever, or just replace it like you can replace your iPhone, or take your car into a car shop and replace a certain part quickly and easily. I mean, maybe that'll change eventually in space. I've heard that they've got these, this machinery now that can go up into space, and it's got robotic arms. You can kind of get it to a satellite and start doing repairs on it. But that's still, a ways off from being more prevalent. So because of that, from the ground up, the design has to be reliable. You don't want your capacitor to fail, because then your whole mission's kind of at risk there.
Yeah, that really puts the term mission critical into a good perspective. Failure is not an option.
Exactly. So, right. Yeah. You don't want to invest millions or perhaps billions of dollars into a space mission only to have it not function by the time it gets to where it needs to.
Especially fail because of a simple capacitor.
That would not be good.
So since we already kind of talked about the applications, so where are these high reliability tantalum capacitors used, and what can engineers learn from those types of applications?
Yeah, sure. So we've got our customers telling us that the high reliability is used in class 1, class 2 space missions. They're used in many applications like radar, lasers, high-powered lasers, communications, avionics, and like I was mentioning before, when you're designing these in, if your end customer is telling you, hey, this product you're designing, we're not exactly sure if it's going to be used at freezing temperatures or if it's going to be both used at freezing and really hot temperatures, you may want to consider using high reliability product that's gone through proven testing, where we do life testing at high temperatures, we do screening at low temperatures and high temperatures, because then that the product that we're giving you has seen those conditions before you start to use it, and that way you can feel assured that whatever you're producing for your end customer will meet those requirements. And you could do that kind of at the board level too, but sometimes you probably don't want to take that risk. If you've got a commercial grade product in something that's meant to go into those extreme conditions, you might maybe I don't know. You might be able to get away with it for your proof of concept, but then long term when you're building a lot of these boards, you know you may not be able to depend on the same level of reliability as you would on a high rel product.
I mean, to be fair, if you think about military and defense, I wouldn't want to hear the term. We might get away with it.
Yeah, exactly.
You do want to have some good reliability and know that
right.
if they push the button, that rocket launches. So
right.
Getting away with it is probably not a good term.
No, and we build that. I mean, we know that Chemet has got a long heritage with working with the military primes, defense contractors. We know what those flow down requirements typically say in them. So one of the big primes may require testing according to mil spec such and such. And because we've been working with that so long, all of those requirements are kind of inherently built into the normal testing that we do here in Simpsonville. And so you can be more assured that what we're building, what's coming out of this facility, it has a better chance of meeting those requirements that the end customer will want in the long run anyway. And so, you gotta kind of think about it as an investment of sorts. You can get a commercial product and then, send it out to a test lab and have it upscreened and then, have it sent to another test lab to check for, like a physical analysis and whatnot. Or, you can just kind of pay for it up front. We do all that here, and we'll be able to provide that sort of data for you so that you can provide to your end customer as needed, rather than having to pull and source from multiple different things and keep that all under control yourself. It's something that we're specializing in.
So it's much easier to take a product that has already been built from the ground up to meet those test requirements,
exactly,
rather than buying a commercial product and seeing if it can meet those same test specs.
Exactly.
Because at the end of the day, you end up with so many failures that you probably can't even purchase the product at this point.
Right.
A simple reel of 10,000 units, you might end up with 1,000 products.
Yeah. So
that wouldn't be very economical. Yeah. Well, we learned about different reliability levels today. We learned about different screening techniques that we have. And we talked about how the Tantalum capacitors are really a different design from the ground up. Mm-hmm. So before we close out, I want to ask you one question. So if you had one piece of advice for an engineer designing a high reliability application, what would that be?
Yeah, I'll based off of just what I was saying, think of high reliability as a long-term investment in your design. You will be investing a little bit more upfront. I mean the cost, the prices of the high reliability are going to be higher than commercial grade. But what you're doing is you're reducing the risk of failure. You're reducing the risk of the work that you're putting on the rest of your team to justify the use of a commercial or an automotive grade product. And in the long run, you may be saving your company, the costly repair work or justification if something goes wrong with another product and they have to do reservicing or whatnot. You're investing in that upfront, and so that would be my advice is consider that when you're doing your design. You may not be getting the highest CV cap and voltage value with the high reliability, but you're getting a robust, highly reliable design, a good product that you can count on, and something that may save your company a lot of heartache in the long run.
Yeah, especially. I mean, when we start talking about high reliability applications, Tantalum in mil-perf specs and high reliability grades is definitely the option for you to choose. So we dove in today into some of those details, what that means for high reliability products to exist. And until next time, keep on asking why.